Pleased to have Professor Lynn Russell from the Scripps Institution of Oceanography. So it's time to get now above the ground, get into the air.
Thank you for the invitation to be here. I am now an oceanographer by trade, even though I'm a chemical engineer by training. I guess a bit of a lapsed engineer, but I'm excited to be here addressing an audience of engineers because this is a problem that does require an engineering perspective. I went to Scripps in 2003 largely because of both the pioneering work of Charles David Keeling, which Eli showed earlier, measuring CO2 for the last 50 years, without which we would still be debating whether we have actually changed the atmospheric CO2 concentration, and because of Paul Crutzen, who did receive the Nobel Prize in 1995 for his work on the ozone hole. So in 2007, when he said we should actually do research on geoengineering, this person who's rarely wrong, it did cause me to start thinking about geoengineering, even though this is not my main area of research. And one particular reason it's important these days is because this, the Arctic region is very susceptible. Recent estimates a month ago suggest that sea ice loss could be substantial by the year 2015. That's 15, right? And so all of a sudden it's much more immediate and in my lifetime. And this is the fun part of being an oceanographer, as long as you don't get seasick. This is north of Ny-Ålesund, north of Norway. And it's one of the beautiful regions that may change substantially in the short term. Both Eli and Armin have introduced the Earth's energy balance. I do like to put this in an engineering perspective term, starting with the first law of thermodynamics that tells us that the energy from the sun has to equal, the shortwave energy coming in has to equal the longwave energy coming out from the Earth. So incoming short equals outgoing long. We're going to ignore the sources and the sinks, even though there is the biggest sink, as was mentioned earlier, is the ocean. And I'm at an oceanographic institution, but we can just ignore it for now. And don't tell anyone I said that. And so, so what's happening here? So we know that the amount of energy coming out, the long wave, is given by the Stefan-Boltzmann law. And so we have it being proportional to the temperature of the surface to the fourth if you assume the Earth is approximately a black body. And what changes that? Well, so if you just had this law, you would find the mean temperature of the Earth is about 30 degrees colder than current temperature, which would make it fairly uninhabitable with current life. But fortunately, we have a greenhouse effect whereby some of this long-wave radiation comes back in. CO2 has enhanced this as, again, this isn't new information. This is based on work from the mid-19th century. And then what I'm going to focus on is changing this part, that we actually don't get the 346 watts per meter squared from the sun because about 30% of it is reflected back by the reflective properties of the surface, essentially the whiteness of the Earth, the non-black body part. And so that's where aerosols come in addition to surface features. And so that's what I'm going to focus on. And so this is our simple model of how both solar reflection methods, SRM, that's apparently sounds less Orwellian than solar radiation management, so this is the new PC term. And so this means we're changing this albedo effect. And so this is the albedo. It's the amount you subtract from the incoming solar luminosity. The greenhouse effect, which I've just put in here as a little f, if you're going to do carbon dioxide removal, what you do is you'd reduce that term rather than trying to increase this term. But this is our current mean temperature. Adding aerosols cools the planet. Removing CO2 also cools the planet, but with the important caveat that was mentioned earlier that these are long wave and solar radiation is short wave. And so the Intergovernmental Panel on Climate Change in 2007, in the report along with Al Gore won the Nobel Peace Prize, summarizes greenhouse effects in this way: carbon dioxide, methane, N2O, tropospheric ozone, give you warming on the order of 2 watts per meter squared increase in that 346 incoming solar. But these are, again, in long wave changes. Solar radiation methods increase the albedo components, the surface albedo by whitening the Earth, or there's 2 aerosol effects. And the difference here has been pointed out is with these you're reducing carbon dioxide or other greenhouse gases. And so you're going sort of closer back to where we started at 0 here, because these are anthropogenic perturbations, and so that's why they're less risky. On the other hand, with the solar radiation, you're actually trying to increase our current cooling effects from aerosols and other things. So you're going further from our known observations and conditions. And then, of course, the other thing I want to point out, uncertainty was mentioned. This is the IPCC's estimation of uncertainty for the effect of aerosols on clouds. You'll note that error bar is larger than the actual effect, right? And so this, I think, is great. A great way to have job security, because we still have a lot of work to do, but it's not necessarily a good way to think about saving the planet. So I'm just going to start out with first some historical context, as well as then I'll present some recent model simulations of cloud brightening. I'll show you our recent experimental results, as well as then talk about the implications for climate engineering. So this is the Toomey effect, it's called. It was proposed in 1974 in this form at the University of Arizona by Sean Toomey. And essentially what he said is if that drops in clouds form on nuclei, they're aerosol particles big enough to take up water. Clouds scatter light. That's how they reduce the incoming solar light. And if you add more particles, you make the droplets smaller and more numerous, which happens to make the clouds brighter. We call this the cloud albedo effect. And it essentially, qualitatively, was solved in 1974. And we have these great pictures from satellite that show this effect in action. The scale here is about 200 miles. This is over the Pacific Ocean. The entire ocean is covered by low-lying stratocumulus clouds. And each of these corresponds to a large cargo ship transiting the ocean. And they're not drunk as they're driving. They just get windblown as the tracks go. So they're going straight, and they're at the point here, but their older track gets blown by the wind. But you can see they're substantially brighter. And this is you can't actually see these with the naked eye. So if you're flying over, don't try and look for them, because this is specifically a very narrow bound wavelength that the satellite measures at 1.8 micron. So the context here, and to address this issue of engineering, I certainly think this is engineering. This is all part of engineering. Combustion engineering, before the 1950s, but certainly since, has led us, with increasing population and consumption, to increase our production of greenhouse gases, including carbon dioxide. And initially, it also increased our aerosols, the aerosols that give us a natural solar radiation management. But we were breathing those aerosols, and so for good air quality engineering reasons, we have reduced aerosols. And in industrialized countries, including the US, this is sort of the trend now, that we actually aren't increasing aerosols, even though our CO2 emissions have continued to go up. Fortunately, China is still increasing aerosols, so they're still giving us a little more cooling, but we are already engineering and climate engineering in the planet we have. And it was the question earlier about, well, it would be great to do a lab scale test case so that we didn't have to live through the consequences. Unfortunately, we don't have the extra planet to do that on. So here are the model simulations that have been run, and this is work by Phil Rasch, who was at the National Center for Atmospheric Research. He's now at Pacific Northwest National Labs. At the top here is his model's prediction of doubling carbon dioxide and the difference from the present-day base case. He gets an overall global warming of 2 degrees Kelvin, and then the colors here represent how much warming in different regions. So this is going beyond my simple box model. and looking at where you actually get warming. And what you can see is between 2 and 4 here is most of the northern hemisphere, and as well as essentially all the inhabited continental space. And so if you put particles in 20% of the seedable clouds, which are mostly we'll see down here and up here, you'll get both regional cooling in specifically those areas that you modify, as well as you'll change other regions too, because you have non-local impacts to changes in albedo. And then down here is actually 70% of the maximum possible seeding. And what you can see is you actually sort of overcool some places. You're getting down to -3 and -4 over Alaska and northern Canada here. And you're not necessarily accomplishing anything else that's very useful. And so this is probably a good target if you were trying to address most global mean temperature problems. We can't, of course, address precip problems on average with this technique because we're only offsetting a long wave heating with a short wave cooling. But one important thing that we could do, which is relevant to this 2015 issue of Arctic sea ice, is that certain areas may be able to be targeted if we can address the uncertainties currently. So this again is doubled CO2. This is the calculated sea ice loss in the Antarctic in March and the Arctic in September. And so this is about -0.5 as a fraction of the control sea ice, so the current. And so you're losing huge amounts of sea ice in both regions. At 40% seeding, you get substantial reduction of those losses. So that's actually higher than the previous case. So to target the Arctic, we might well justify 40% seeding. Here you actually get an increase in sea ice in large regions. So again, that would probably be more than one would need to do. But somewhere between 20 and 40% could be a useful way to reduce the point at which sea ice might be drastically lost. And I'll just point out there's 2 reasons one wants to do this, and that may explain their color scheme here. In addition to sea ice being great for polar bears, nothing against polar bears, but the main thing is sea ice is white. And covering a dark surface, that's an additional surface albedo contribution. So when you start to lose that fraction, even at the far North Pole, it does have feedback so that the loss of sea ice actually causes additional warming that we would want to avoid. So, if this all sounds great, so what do we need to do? Why don't we just go ahead and do it? Well, that was all modeling. And in this same paper that those results came from, they point out that there are large nonlinear interactions that are still not understood, quantified, or verified in their relative importance compared to the Toomey effect, and those need to be assessed. I'll mention just one of them from this study by Korhonen and al. From Finland, where what she points out is that not only do you change the reflectance of the clouds, you actually change the cloud microphysics and what we call their supersaturation. In other words, the relative humidity minus 100%, the degree to which they exceed saturation humidity. And so what has been shown here is that in these regions that you target, you reduce the supersaturation, and that kind of offsets part of what you're trying to do. So in light of these modeling results for the potential of this technique, we are even more motivated to better understand the uncertainties of the Toomey effect, which is currently happening with pollution from those ships I showed earlier, as well as cities emit enough pollution to change stratus cloud effects. And so mostly to understand those basic physics of clouds, we designed the Eastern Pacific Emitted Aerosol Cloud Experiment to look at controlled emissions of particles and their effects on clouds using aircraft and using the aircraft to sample those cloud droplets, as well as satellites to see how the cloud reflectance changed at the same time. And so we had a small research ship, and we ran it in a pattern to create a track. The wind blows the track. This was a large collaboration with Scripps, Caltech, as well as Armin Sarusian are at University of Arizona. Where did we do this experiment? Well, we had to go where we had the most probability of having the low stratus clouds that are affected by these particles. And these are the 3 regions of the world where you get 30 to 40% daytime stratocumulus cloud amounts. So we based our experiment largely for logistical reasons in the cheapest of those, which was Monterey. How did we go about controlling particles for emission? Well, in retrospect, we may have been inspired by these early studies that used artificial plumes from smoke oil to track the dispersion of plumes from smokestacks. This was work from Brookhaven National Laboratory. We did a slightly more modern version of that. We used US Army smoke fog generators that are circa about 1980 production for battlefield obscuration. Their eBay price, which was more than they were worth, was $100 each. We bought 4 and got 2 of them to work with the parts of 4. And I wouldn't want one on a battlefield. But, and then we used actually Shell Diala, which is a transformer oil, but fairly similar to paraffin oil used previously. It's about $10 a gallon. That part was not in our NSF budget, so Sea Spray Research paid for that. This is what they look like when they're running. This is off the back of the Point Sur. As you can tell, it's not exactly ideal operating conditions. Lots of eddies from the superstructure because we had fairly low net flow. And fortunately, we had a motorcycle crew chief to keep them running for us. I'll show you more about this later. The plane then could come and sample both this actual plume of smoke and then go downwind and sample the clouds and the actual effects of the smoke particles on the clouds. So 3 questions are relevant to this experiment, or to this part of the experiment. Did we produce enough smoke particles to have an effect? Do smoke particles even make cloud droplets? Because not everything can take up water. And did the droplets actually change the albedo? So the first question was really easy to answer. Here are our generated smoke particles. In the gray here, we made more than 100,000 particles per cubic centimeter are the units here. And as you can see, they're mostly organic in green with a little bit of sulfate. You can compare that composition to cargo ships, which are more than half sulfate. But we made comparable numbers and sizes. So these are mostly below 100 nanometer or 0.1 micron in diameter. And as you can see, that's about a factor of 10 to 100 greater than the marine typical particle concentrations, because the marine areas are, in fact, very clean unless you're behind a cargo ship. So next question, did those particles activate to cloud droplets? And this is where the counterflow virtual impactor that Armin Sarusian's group designed allowed us to sample the actual droplets that are at about 20 to 30 microns in diameter in the cloud. And so these measurements in cloud show you how many droplets we got in cloud from our smoke generator, which is about 300 compared to the background at about 70 drops per cubic centimeter. So that's a lot less than the particles we started with. As you can see in cloud, only a few of them activate to droplets, but it was still fairly comparable to what the cargo ship was doing. And so did we see a track? Yes, we did. This is July 16th. These are tracks from other ships, sort of off to the west of where we were. We were here close to Monterey. This white little track down here was our track, and I've blown that up here. And essentially what we were doing is at 6 a.m. we started emitting smoke and worked our way down this way. This was our actual ship track. And then we did a simple model to project where those emissions would get blown 7 hours later when the satellite overpass took this picture. And so this colored line shows you where those emissions were, starting with the 6 a.m. emissions were blown the furthest south. But you can see the actual track tracking exactly where we'd gone at almost every turn, despite the non-constant wind speed, which we haven't reflected in this model. And so you get a significant brightening of the cloud. We demonstrated we could do this on a controlled scale. And we could measure the change in the cloud droplet as a result of these smoke particles, which were initially thought to not act as cloud droplet nuclei because they were organic rather than sulfate. So they did make cloud droplets, and we did show they changed the albedo on July 16th. How often did they actually change the albedo? So there the story gets a little messier. So in the 31 days of July 2011, there were 22 days that there were tracks observed. And we have no information on whether there were multiple cloud layers. In the 12 days of our cruise, 12th to 23rd, there were only 4 days. So essentially, our 12 days got the 8 non-track days in the entire region. And so only one of those days formed an effective cloud. 7 of those days we know because we measured at the ship, although we don't have measurements for all the days, that there were cloud layers above the layer that the particles were being taken into. And so because the particles did not mix up to the top layer, the satellite and the sun's albedo never actually see the effect of those particles. And so they're not important. So we're now looking at the frequency of these multi-layered clouds, and that's what I've shown here from a Calypso retrieval. Red is 50%, so in all these regions, including the ones we studied and other important cloud regions, you have a high frequency of multi-layered clouds that are currently not included in global climate models. So even though this was not a geoengineering experiment, it's worth noting that 2 things actually demonstrate an observable cooling. The cargo ship at $100,000 a day, most of which goes for 100,000 gallons of bunker fuel oil per day burned, gives you about a nanokelvin of warming amortized over 100 years from the CO2 produced, but actually 2 nanokelvins of cooling from the cloud drops on days that they made tracks. So the cooling to warming ratio is about 2. With our point SIR, we cost $15,000 a day. We did also burn 500 gallons diesel per day, and that's about a 0.008 nanokelvin warming from CO2. But our 200 gallons of oil, which didn't get burned, it just stayed as paraffin oil, gave us a 0.4 nanokelvin cooling. So that's a cooling to warming ratio of about 50. So, and I put high uncertainty bars since it's only a proof of concept. But that's the basic idea, that we think that technology exists if you can get the microphysics to work out. Because, of course, those ratios are only on days that you make tracks. And so this is my 50 seconds of fame, because I actually got named in an article that wasn't in a science journal. And so they were looking at the SPICE experiment, primarily, that Eli mentioned earlier, and actually said that since that experiment got canceled, that they thought ours, even though it wasn't designed for geoengineering, could pave the way for work on geoengineering. Well, I'm not really sure that that's true. It certainly does help to make the point that this is potentially a way to offset some warming by brightening clouds. We can get it to work. We really don't need new technology, so it's fairly fast to implement. There's obviously things you could do better, but you do have to consider the ecosystem impacts as well as the frequency of multi-layered clouds in the region you're targeting. And you really need to think about what global climate model processes don't have. That you actually need experiments to test scale up, that these qualitative effects of aerosols need to be verified experimentally. And so with that, I'll just point out one more thing, which is that in this recent compilation on geoengineering, Chapman and Fox pointed out that they consider aerosols one of the most feasible approaches, and that includes both the cloud brightening I just talked about, as well as what Ben will talk about after the break. And then with that, I'm just going to attempt some high technology here, unless I get run out of time. I will. All right, so I'm clicking on the little QuickTime thing. Help. How do I get it? Oh, do I have to minimize that one?
like we're frozen.
Yep, no movie.
We have 1 minute. We can. Any tips? Frozen.
I'll work on it while you guys do Q&A.
Okay.
Oh,
Okay.
that's a good idea.
So yeah, I think that's the end of my slides. I just wanted to give you a feel for how exciting these smoke generators are to run. But
All right. So why don't we do questions, and Chris will help us out.
Reed Hendershot, Air Products. One of my questions on some of these different engineering methods plus your cloud brightening is they seem to rely a lot on models, which are useful but normally wrong. I do use models a lot in my work, but they require a lot of manipulation, validation, things like that to make them more useful. The climate seems like in cloud generation, we have so little knowledge of it that our models probably not very good. What's your view of the models, these cloud generation models, the models in general for this kind of field?
okay, so yes, the models are very good at some things. The models, I run models, I use models, and what they're designed for and what their results are reported for are pretty good. But you have to keep in mind what they can and can't do. So for instance, the uncertainties on the regional changes in temperature in global climate models are very dependent on the schemes they use for clouds, most of which are fairly uncertain in climate models. You can also use essentially a weather model to predict clouds. And for certain kinds of storms, you actually do pretty well, because these days where a lot of the weather reports are pretty accurate about predicting large-scale thunderstorms and even their timing. So, I don't really have one general answer to how good models are. I think for predicting the sorts of things that I've shown here, I want to just reemphasize my conclusion that they need verification, that we actually haven't, the indirect effects, the reason we did the study is because the indirect effects are one of the most uncertain parts of the model for a number of reasons, including their failure to properly incorporate either multi-layered clouds, which we're currently looking into. That's not even an issue discussed in the literature yet. And then the supersaturation effects are often overly simplified because of the complexity of global climate models. And so, okay, not working, okay.
Hi, Andrea Armani, University of Southern California. Mm-hmm. I have a kind of a quick question, I guess. You mentioned on one of the earlier slides about how you might be able to kind of selectively create hats, I guess, on either of the poles and to protect the poles from, and then not put particles on the rest of the Earth. Has anyone studied the diffusion, I guess, if you put an aerosol in one place, how fast or how long it would stay in that location before it would make it to the equator or some other part of the planet?
Yeah, really good and interesting question. Thank you for that. I think it definitely is part of the question. What I've shown here are actually targeting emissions low in the atmosphere of aerosols. And the lifetime of most aerosol particles in the size range is under a week in the atmosphere. And that's kind of like the half-life, right? And so they start falling out mostly or getting rained out fairly efficiently after that. And so that's one of the things that essentially, as we think about, replacing the aerosols we've taken out of our process, if you want to think of it that way, what we're trying to do is put them in a place where people don't have to breathe them. And so that's the idea by putting particles over the ocean, is that you're largely targeting areas where most of the particles will fall out before they reach populated areas. So to a large extent, low aerosols do have that effect and are fairly easy to turn off and control. The other thing is that by affecting low clouds, you're less likely to change synoptic scale weather patterns that do change both temperature and precipitation in regions far downwind of where you're putting the aerosol. And so that's one of the reasons that I think that's perhaps a safer approach than stratospheric aerosols. There's a lot of other reasons that it's not necessarily better. And even given that, what the impacts I showed you for the Arctic were actually not necessarily focusing the aerosols on the Arctic, but actually seeding them in other places. And I was just focusing on the change to the Arctic and Antarctic regions. So we targeted that approach largely targets the areas with the most clouds on the planet, is what they've looked at so far. I do think you could try and just put aerosols over the Arctic. So that was actually seeding these blue areas primarily and just looking at the impacts on the Arctic from that. It's potentially an idea to try and just put aerosols over the Arctic, but no one's modeled that yet that I've seen. Eli.
Actually, we're out of time, so let's save it. We have a break right now. We will have that panel discussion after our fourth speaker for more questions. So let's thank the first three speakers again.